Hello everybody! Today I'm gonna show you how to check beam members subjected to fire with help of SDC Verifier in Ansys. The standard we're gonna use is Eurocode 3 structural fire design. In this demonstration I'm gonna use the test model which is already created in Ansys 2019 R2. As you can see here, the static structure analysis is already created and linked to the SDC Verifier software. If you still don't know how to start the new SDC Verifier project in Ansys, the relevant video is already uploaded on our YouTube channel. In our case, we just go to the previously prepared model by double-clicking on the SDC Verifier icon. During the opening, we need to choose the required model to be opened and press OK. So now I'm going to show you the model directly, which is actually the Lattice structure, which consists of a lot of beam members with different variations of cross sections. Should be good enough for our example. Okay, so let's go back to our SDC Verifier project. And first thing we need to do is to add the fire design standard in our standards chapter. For that, we need to press right button and load that from the library. If you will select the Eurocode 3 structural fire design, you'll automatically see a lot of items which are used in the standards. I'm gonna go back to the description of that later. So now let's press OK. After it's added, I'm gonna show you the brief overview of the input data to be set up by user, and also overview of the checks which are implemented in this standard. So the first chapter of our input data is the constants. I will edit that to show you the full list. It actually consists of the constant values which are prescribed by the standard, such as partial factor for normal temperature design, for the fire design situation, and so on. By default, it's assigned as the recommended by standard values. But if it's required to be changed by user, you can simply double click on that and replace with the required value. In our case, I will leave it as it is and press cancel to go through the next items. The second chapter is the characteristics, which contains the list of items required to be set up. The first one is the fabrication type. In this window, you need to set up the fabrication type for each property of beam members you have in a model. Here are two options are available. It's rolled and welded. In our case, all members are welded. For that, we need to choose the required option and press to all. After that, press OK. And press yes. This one is done, and the next type is the manufacture method. In this window, instead of fabrication type, you need to assign a whole of manufacturing method for each property you have in a model. In our case, it's cold formed, but if in your case it's hot finished, you can easily reapply it to the selected items or apply that to all. I'm gonna get it back since everything is cold formed. Apply to all and press OK. Again OK. The next chapter is fillet. In this window, you need to set up the values of fillets for the properties which are defined as the rolled sections in the fabrication type. In our case, everything is welded. By these, the zero values are going to be unchanged. Besides, we need to define the material type we have in a model. In our model, we have only the one material, which is named structural steel. And for that, we need to choose steel 355. And then press OK. The next chapter is the uniform temperature. In this window, you need to set up the value of temperature which your structure is subjected to. In our case, the structure is located in the normal environment with the temperature value of 20 degrees Celsius. That's why we need to set up that to the whole structure. You can make sure on that because we selected the all entities here. Our columns are going to be subjected to the temperature value of 400 degrees. To choose them, we need to go to the SDC Verifier selector, then go to the beam members section, again beam members, and choose them from the list. Our columns consist of the first 6 beam members which are recognized in the Beam Member Finder tool. If you don't know for some reason how to use the Beam Member Finder tool, you can always go to our YouTube channel and find dedicated video on this topic. After that, we need to press OK and assign value of 400 degrees Celsius. And again OK. The last 2 chapters define the adaptation factors for the non-uniform temperature distribution across the cross-section, it's K1, and along the beam, it's K2. Let's start from the first one. As in the previous time, we need to define selection and to assign to it the allowable options in this window. In our case, the whole structure, which is actually all entities, is exposed on all 4 sides, which in fact gives us the adaptation factor of 1, except of the 6 beam members, which are our columns of the structure. They are protected beams exposed on 3 sides, which gives in fact factor of 0.85. After it's assigned, you need to press OK. In the second chapter, we gotta choose the whole structure, because actually this adaptation factor 2 in our case should be taken into account only at the support of the statically indeterminate beams. But if you have the other case, you can always choose this option as well. After it's assigned, you need to press OK. That's basically it regarding the items which depend on the user's decision. And before I go to the checks chapter, I'm gonna give you also the brief overview on the last section from the input data, which is standard tables. It consists of the 3 tables which are prescribed by the Eurocode tree. The first one is the imperfection factors to be taken into account at the normal temperature design. And the 2 last are extremely important because that's are the reduction factors for the effective yield strength and also for the slope of the linear elastic range. Here is no reason to change these values because that's the standard ones taken directly from Eurocode tree, and it's completely open to the user for the brief overview and automatically taken into account in the all checks which are going to be explained later on. And now it's time to go to the checks. This chapter contains the list of checks which are divided over the 2 categories. It can be recognized by the different icons. The first one is the property check. This type of check doesn't depend on the calculation outcomes, but it gives possibility to determine a geometric property for a given cross-section used in the design of beams or structural members. It can be the different thicknesses, areas, shear areas, and so on. As you can notice, the first 4 property checks are divided over the different types of cross-sections. In this case, it's handy to find the relevant chapter you're interested in. But in addition, the 5th property check is added and contains the main common data for the all properties. And the last property check defines the flange classification with the different limits as the intermediate steps required for that. To get the data which I mentioned about in these checks, the standard table needs to be created by pressing the right button and choosing the Table Expand Extreme option. Then you need to fill the table, and all the parameters which are contained in these checks will be shown in this window. In our case, it's the shear area, diameter, thickness, epsilon, lambda, classification, and so on, and it's shown for each property you have in a model. After that, you can save this table with the customized name. And also the description can be added. And then press OK. As you can see here, The table is saved in the table section. This approach is applicable to the all property checks in this chapter. And now let's go to the second category of checks. I will walk through each of them with a more detailed overview. And the first one is the classification. This type of check defines the highest class among the web and flange classes. It's important also to remember that Eurocode 3 member check standard supports verification of the section that belongs to classes 1, 2, or 3, and class 4 is out of the scope. This automatically calculated classification is further used in the next 7 checks, which in total are the member resistance in the different load situations. And the first one is the Axial Check. It's required to be executed in case of your beam members are subjected to the axial forces, tensile or compressive. I will edit that to show you what is inside and will go through the full calculation procedure. To do that, you need to press the right button and then press Edit. The open pop-up window is also typical for the all further checks, except of the data inside of this window. It consists of the title, which is Axial Check in our case, alias, which is Unicode name for this check, description as the short reference to the chapter in the standard, which corresponds to this check, and the list of parameters. The parameters are actually the intermediate items which are required to be used in the formulas and also can be displayed in the tables and plots. Each of these parameters consists also of title, alias, description with the reference to the standard, and formula itself. So it's extremely useful to see everything opened. After the full calculation procedure is done and the design tension resistance is computed, the good visualization of outcomes can be presented by the additional calculated parameter, which is utilization factor. This parameter shows the ratio between the designed axial force in a model and design tension resistance. In fact, it should not exceed the value of 1. Then your outcomes will be within the allowable limits. This option is actually implemented for each of the next checks. The next check is the buckling compression resistance. This check is separately created to show you the buckling risk of your member under the compressive force. As the result, it also shows you the utilization factor, which is ratio between the actual compressive force and design buckling resistance of a compression member. Pay attention that it shows you the absolute maximum value over the two local directions of the cross section, major and minor. However, both options are available to be shown separately as well as each parameter inside of this check. As you might notice, the beam buckling length is used in the formula for the elastic critical force, which is later on used for the determination of the non-dimensional slenderness at room temperature. It means that the buckling analysis is impossible to be executed if the beam members are not recognized in the beam member finder tool of SDC Verifier. The next check is the bending check. It shows you the strength level of the beam member under the bending loads. It's represented by the utilization factor as the ratio between the bending moment and the design moment resistance of the beam member. As in the previous check, it can be represented by the local directions of the beam member, major and minor, and the absolute maximum value over the two directions. Of course, as in the previous checks, the other parameters can also be displayed. The next check will help you to verify the laterally unrestrained beam members which are subjected to the lateral torsional buckling risk. The outcomes are also represented by the utilization factor, which is in this case the ratio between the bending moment and the design lateral torsional buckling resisting moment. This check requires the recognized beam members, since the lateral torsional buckling length is used in the formulas. The next chapter is the shear check. This chapter contains the calculation procedure to make sure that the beam members have no risk in the shear resistance. The outcomes also can be represented as the utilization factor values in each direction, major and minor, and as the maximum absolute value. If the beam members are subjected to combined bending and axial compression, the compression and bending chapter needs to be used. The outcomes in this case are represented by the combined value of utilization factor, which consists of two values above, depending on the classification type of cross-section, 1 or 2, or third type. What is also important to know is that depending on the distribution of equivalent uniform moment in the beam members, the extra beta M factor needs to be taken into account. In SDC Verifier software, it's automatically calculated and included in the formulas. So here is no extra efforts are required from the user side. To make life easier in the processing results, an extra check is added. It's actually a resistance overall, which contains the all utilization factors which were described before. It's related to the axial check, buckling compression check, bending check, shear check, lateral torsional buckling check, and combined check. If you don't want to keep fixating on these separate values of utilization factors which are shown over a certain direction or the absolute maximum value, the last utilization factor can be used. This value is different because it shows the maximum values over the all checks of utilization factors above. For example, if the beam member has the utilization factor for the axial check of 1.2 and for shear it's 1.1 and for the other checks it's below 1, then the maximum value of 1.2 as for the axial check will be displayed. Of course, this chapter is extremely useful for making the expand tables over these utilization factors. In this case, you can easily track if your beam members are within allowable limits at certain verification. So now I'm gonna make a brief overview on the calculation itself. So the first thing we need to do is to go back to the Ansys model, and I'm gonna walk through the loads applied to the model. First of all, that's of course the gravity load with the standard value of acceleration. That's the nodal rotation and nodal displacement at the bottom points gives us the fixed constraint. And the first down means that the first is applied at the top points in the vertical direction to the bottom, and the first top is applied to each node of the top side of the structure. We also have an additional applied side force at the middle nodes here in side direction. In our case, it's -y. So all these loads I'm gonna combine in the individual loads in SDC Verifier software, in the job, which is static structural. Here we have all these loads, and here a couple of load sets are already created. Partial load factors are assigned to each of the individual loads with the value of 1.35, and for gravity is 1. All the load sets are combined in the load group, which gives the envelope of the outcomes over the load combinations. So it means that if you have an extreme value of outcome from the certain load set, it will be included in this load group for each element. And after that, we need to execute analysis. It takes actually a couple of seconds, and after analysis is executed, the relevant outcomes are received and attached to the individual loads. It's almost there. Yes, it's done. And now the only thing is left to do is to go to the standard directly and execute the required checks. So the first check I'm gonna do is the Axial Check. I will create the component extreme table over the all beam members recognized in the beam member finder tool. For that we need to press here, beam members from the list. Then press all and press OK. The outcomes will be shown for the load group, as I explained before. We need to fill the table. And here you can see that the results are presented for each beam member over the different parameters. The reduction factor in this case is 0.47 only for the 6 first beam members, since the uniform temperature load is 600 degrees, when for the other part of the structure it's the normal temperature with the value of 20 degrees Celsius. That's why the reduction factor is 1 for them. The other parameters are also displayed here, as the actual force, design tension resistance, the total resistance, and the utilization factor. So here we can notice that for the beam member 23, the utilization factor is 1.12, which means that it exceeds a allowable value. The same situations with the beam members 71 and 72. They have the utilization factor value of 1.21. To visualize these outcomes, we're going to create the plot. Press right button, criteria plot. We're going to choose all entities as the whole structure and the load group. Then preview the plot. The good picture is given in the Ansys mechanical. Please pay attention that by default Ansys uses the legend range as the arithmetic one. That's why we're going to change this value with 1, and it means that the all beam members which are colored in red are actually overstressed and does not pass the check. In our case, these are 3 members. The same calculation procedure is applicable for the other checks. So let's go back to the SDC and to verify structure according to other checks. And the next one is the backlink compression check. We're going to create the same table as the last time. Then press fill table. And again, all the parameters are shown for each beam member. It's a quite detailed overview. And again, here you can see the list of utilization factor, absolute maximum values, which is really important for us. Here I noticed a couple of elements are overstressed with the value of 1.5 and 1.49. For the good visualization, the same plot can be created. Criteria, and then preview. From the beginning, I'm going to change the legend range to set up the value of 1 here, and it means that the all elements which are colored in red again are overstressed and that does not pass the beam backlink compression check. So in the Axial Check we had 3 overstressed beam members, these 2 verticals and 1 small horizontal, but for the beam backlink compression we also have overstressed diagonals in this case. And the main columns are actually okay. Let's go to the next check in the main menu. It's going to be the bending check. I'll create the same table, beam members, all, press OK, fill table. And again, all parameters are displayed for each beam member. So most of the beam members are okay except of the list which is colored in red. I'm going to display that by picture. Criteria upload and preview. Again, from the beginning, I'm gonna change the legend range to clearly see which members are overstressed. And in fact, these are only the members on top of the frame. Add the members connections. Let's go through the other checks. But before, save the criteria upload. So the next chapter is the lattice torsional buckling. Again, I'm going to create the component extreme table for the all beam members. Fill. It's calculating. And the standard window is displayed, including the utilization factor. Several elements are still overstressed, and I'm gonna show them by criteria plot. Utilization factor and preview. Again, it wants to change the legend range to clearly see the overstressed elements. And as for bending check, it's similar. It seems like the top members are overstressed and do not pass the lateral torsional buckling check. I'm gonna go back to the shear check. The same procedure. It's calculating. It's also nice to know that the building progress of the table does not take a lot of time. So here we have actually quite low values of utilization factors, and we see that the whole structure within allowable limits. I'm gonna save it, and traditionally we can create the criteria plot. Let's go to the mechanical. So for shear, you can see the relatively higher utilization factor values on top of the structure. And here at the intermediate beam, where we have actually eccentricity due to the diagonals. All right, let's go back to the other checks. First, save the plot. And the final one is the compression and bending check. The same procedure. Field table. Again, it takes a couple of seconds and we're done. All parameters are shown, including the combined utilization factor. I see a couple of beam members are overstressed, and I'm gonna display them by using the criteria plot. Combined, all entities, preview. Let's go to the mechanical. Slightly changes in the legend range, and here we can see the combined utilization factor. So still we have the high compression in the diagonals and also in these small members, and on top of the structure the list of the member is overstressed. That's actually a good visualization, but what is really handy to see is the last chapter, which is the resistance overall. First of all, I'm going to show you the expand table over the beam members. And pay your attention on the parameters are going to be displayed in this window, because they are actually the utilization factors which were shown before, of course over the different directions. So the total utilization factor for the Axial Check, let's go down. Here you can see the same value of 1.12, 1.21. Utilization factors for buckling compression in two directions, major and minor, and the absolute maximum one. Let's go down to walk through. So it's still 1.22, 1.5, the same value as it was displayed. The same situation with the bending check, the absolute maximum for shear check, lateral torsional combined, and important is in this case is the utilization factor overall. You might notice that it shows you the maximum value over the all utilization factors in this chapter. So for beam member 1, the maximum value is, we're going on the right side, so now it's 0.24, and here we have 0.4 for the combined, and it's already displayed in the utilization factor overall. So it's nice to see whether your structure is okay or not okay. Except of that, it's also possible, of course, to plot that by using the criteria plot. The only thing we need to do is to choose the appropriate utilization factor here, and then preview. Traditionally, a slight change in the ladder range. And the overall checks are displayed in the one picture. That's extremely useful to know whether your element's okay or not okay at a certain parts. So here you can easily track and visualize all the checks in one picture. But I'm going to show you also the influence of the temperature, of the non-uniform temperature on the structure. I will go back to the SDC Verifier icon, to the input data, and to the uniform temperature in the characteristic chapter as we went through this. So previously we assigned the temperature value of 600 degrees Celsius for these vertical columns. For all vertical columns. It's actually possible to highlight them in the model. So it's colored in yellow now. And now I'm going to change this temperature value with the value of 1000 degrees Celsius. Pop-up window occurs and it shows you that all your the results from all of your checks will be cleared in that case, because you're going to change the input data. I'll press OK. Then go back to the resistance overall plot, and I'll display the same plot. For the moment, all checks require to be calculated once again after the input data is changed. It's not a big deal because the whole calculation workflow take not more than I don't know, 20 seconds for the moment. That depends on your model. So we're almost there. And it's already displayed. So here you can clearly see, by the way, we need to change the legend range. You can clearly see that for the moment, all of your vertical columns are overstressed after the non-uniform temperature is changed. The values for that are approximately, at some location it's more than 3, so it's close to 4. So this depends on location, but in total, yeah, that's overstressed. I'm gonna change the temperature as well with the value of 800. Apply, press OK, again OK, and again preview the plot. So by using this approach, any extra efforts are required from the user side. The only thing which needs to be set up is the input data and actually the loads. The rest of procedure will be executed automatically. Let's go to the mechanical. Let's change the legend range. And here you can see that the values are significantly reduced. So that's basically it regarding the complete calculation workflow of Eurocode 3 fire design standard. But if you still have any questions, you can always get a quick support by using the Help chapter in SDC Verifier menu. Thanks for watching.